All right. Cool. So hi everyone. Today we'll be talking about prime factorization. So this is something that most of you are probably familiar with, but there's a few interesting tricks, two tricks that we'll be showing you, specifically finding the total number of factors and the sum of factors. So back to, okay, I know everyone here is an expert on prime numbers because Coach Owen was able to give you a lecture about that. And yeah, everyone knows what prime numbers are, what composite numbers are. Um, does anyone want to give me what a prime factorization is? So what is prime factorization? Um, please send me some of your answers in the chat. Like what comes to mind when you think prime factorization? Coach Owen, you can go to the next slide. Maybe this comes to mind. Yep. Any other suggestions? I got like all the factors are prime. Keep factoring until there are only prime numbers. Yep. So as people are suggesting, you might, so this is a prime factorization kind of tree. And what you might do is, so you can see that you start with 680 and you try to find two factors that multiply to it, so 20 and 34. But then you can break down these factors even further into what multiply into them. And so you have 4 times 5 times 17 times 2. And then once you get to all of the all the factors that are prime, you can see how many there are. So you can see at the bottom, one way of writing the prime factorization is with these exponents. So there are 3 2s, so 2 to the third, 1 5, so 5 to the first, and 1 17, which is 17 to the first. So if you multiply this all together in their exponent form, you'll get back to 680. So this would be the prime factorization of 680. Does it make sense to everyone? This is probably review for most of you. If not, it's fine too. All right, so let's go to the next slide. So something that we need to know before we move on is the 0th power. So everyone, please send me in direct message what the result is for each of these. So what's 10 to the 0, 5 to the 0, 21 to the 0. All right, so I think everyone got this basically. The answer is, for each of these, the answer is, next slide, 1. So, yep, anything to the power of 0 is 1. And I wonder if anyone knows why. It might be a little tough to send me in chat, but you can try to. But I'll also go over kind of one explanation I really liked.
I think someone raised their hand.
Okay. Alrisha, would you like to give an explanation?
So I kind of already like learned this.
Uh-huh.
So basically, I think like for power you do like the number times itself, and then like for something to the power of 1, it's I mean, yeah, it's just itself. So basically, if you look at it, you can find the pattern is that like for example, 3 to the power of 3 is basically 3 to the power of 2 times 3. So basically you can use division to like go backwards. So if you know 3 to the power of 3, you can divide that by 3 and then you figure out 3 to the power of 2. So 3 to the power of 1 is 3. So then if you divide that by 3, which is 1, that's 3 to the power of 0, and then that's how you know it's 1, and it works with everything else because a number divided by itself is always 1, and you can also use that to figure out negative exponents.
That's exactly the explanation that I like. And let me just show you in one way. So Coach Owen, you can go to the explanation and we can see. But yeah, that's perfect. So if we can go to the explanation, I think you're going ahead in the slides. Okay. So yeah, basically, if you're dividing exponents, so if you have 3 to the power of 2 over 3 to the power of 1, you subtract the exponents. So 3 to the power of 2 over 3 to the power of 1 is 3 squared over 3. It's 3 times 3 over 3. And you can cancel out the 3's and you have 3. So 3 to the power of 2 over 3 to the power of 1 is 3 to the is the same. When you have exponents, you subtract them. So 3 to the power of 2 minus 1. So that's 3 to the 1, which is just 3. So in general, the rule is subtract exponents when you're dividing them. And if you think about 3 to the 1 over 3 to the 1, then that's just 3 over 3, which is 1. So if you subtract the exponents, 1 minus 1, that's 3 to the 0. So exactly as Alrisha said, you can just subtract the exponents. So does anyone know then what would 3 to the negative 1 be? Kaden?
1/3.
Why would it be 1/3?
Because you would divide 1 by 3 again, and then you would get 1/3.
Yep, perfect. So let's say you even had like 3 to the 0 over 3 to the 1. You subtract the exponents, it's 3 to the minus 1. And also 3 to 0 is 1. 3 to the 1 at the bottom is 3, so it's just 1 over 3. So, yep. So,
Give me a second. Let
that's
me
why.
share that explanation. I think. we
Okay.
found it.
Cool. So in case people weren't really following,
I see. Here you go.
yeah, so this is exactly basically what Alrisha said. You have 2 to the 5th over 2 to the 3rd. This is just showing that you subtract the exponents. So you have 5 2's at the top, 3 2's at the bottom. You can cancel out each of the 2's and you get 2 squared. So in general, the rule is if you have 2 exponents, it's the same as subtracting. So 2 to the 5th over 2 to the 3rd is 2 to the 5 minus 3 is just 2 squared. So if you think about it, then if you have 2 over 2, which is 1, we know that. That's also 2 is also 2 to the 1st. So you can also write it like this. But then you can also subtract those exponents. So you'll get that 2 to the 1 minus 1 equals 1, which also means 2 to the 0 is 1. So that's a quick proof of how it works. And yeah, so let's go back to prime factorizations. All right, so we're going to do an exercise which is counting the number of factors. So the question is, next slide, how many factors does 680 have? So everyone, I think you can try this and let me know what you get. I'll give you about 2 or 3 minutes.
Is it only prime factors or like
Yeah.
every factor?
That's a great question. So factors, in this case, it doesn't say prime, so that could be any factor. So you can see 20 is a factor, 34 is a factor, 4 is a factor, right? So anything that divides evenly into 680. That's a very important thing to know. And honestly, a lot of times in math competitions, if I just misread the question, I'll get it wrong. So it's important to know prime factors versus factors. Great question.
Oh, did you put it in the chat?
Sorry, yeah, you can send direct message me. All right, so yeah, this is a pretty difficult question. Let's start going over this. Kaden, would you like to give what you got?
I have a question. Couldn't you just find all the combinations of the prime factors?
I think that's a great idea. What do you mean by that?
Like because there are 5 prime factors of 680, so you could just find all the prime, like the combinations of prime factors that you could use.
Yeah, I think that's a great idea. So to go off of what Kaden said, you basically want some type of combination of the prime factors of 2, 5, and 17. And you only have at most 3 2s, at most 1 5, and at most 1 17. So one way of thinking about this is you can write out, like you have 4 different possibilities for 2, 2 different possibilities for 5, and 2 different possibilities for 17. And you can see that every single combination of these choices for 2, 5, and 17 will create a different factor of 680. So for example, if you multiply 2 to the 0, 5 to the 0, 17 to the 0, those are all 1, right? So that's 1. And 1 is one of the factors of 680. Another possibility is 2 squared times 5 to the 0 times 17 to the 1. And that gives you, give me a second, that gives you 68. So yeah, each of these different paths will give you a unique factor of 680. So one way of figuring out how many factors are there for 680 is how many paths are there here. Does anyone want to send me direct messages of how many paths there might be here? So yeah, please send me a direct message instead of how many factors are there, how many paths are there? And actually, it's the same answer, as you might see. So as you're figuring out how many paths there are, you might want to think, what's an easy way of counting how many paths there are? You could try each one. That's one way. Let's get some help from one of your classmates. So, Arisha, would you like to explain your reasoning for what you got?
I got 16. I was kind of guessing, but I saw that 2 had 4 of the different powers, and 5 had 2, and 17 had 2. So I just did 4 times 2 times 2.
It's a great guess. Yeah. Kaden, do you want to also give an explanation, or maybe it's the same?
So I saw that there are 4 different possibilities for 2. So I could just find out one of them and then multiply it by 4 at the end. And then I just counted how many paths there were for 1 and then multiplied that by 4.
Yeah. So in the end, yes, it's right. So you should just multiply all your choices. Maybe you've seen problems like this, but sometimes there's like, oh, how many different 7-digit phone numbers are there? And there's 10 different digits, right? So what you would do to figure out how many different 7-digit phone numbers there are is to multiply 10 by 10 by 10 by 10 7 times, because there's 10 choices in each one. So when you're trying to count how many total things there are, you usually would be counting, you'd be multiplying how many there are. So you can think of it like there's 4 different paths going from 2 0 to 1 2 2 2 3 into 5 0. And there's also 4 different paths going from 2 0 to 1 2 2 2 3 into 5 1. That's a total of 8 going into from 2 to 5. But then with every single one of those paths, you can either go to 17 0 or 17 1. So you're considering every single one of those 8 paths, and now you're multiplying 2, because you will either go to 17 0 or 17 1, and that'll create a new path. So yes, every time you're just multiplying each of these. So the correct answer, as Alrisha, Kaden, most of you got. Kaden, would you like to say something?
For the 7-digit whole numbers one, would it actually be 9 times 10 times 10 times 10? Because the first digit cannot be 0.
Yeah, I think if you have that requirement, then yeah, that's right. I'm not sure. It depends on how the question is. Sometimes if it's a phone number, I guess you might be able to have like a 0 at the beginning. So it depends. But if it's like how many 7-digit numbers are there, then 0 would make it so that it's not a 7-digit number. So that's something to think about. That's definitely something to be careful of. So great point. All right, so let's continue. So the general rule, as you saw, maybe we can go back to the slide above, is you take each of the exponents and you add 1 and they multiply. So you have 2 to the third, that 3, you add 1 and you get 4. 5 to the first, that 1, you add 1 and you get 2. And then 17 to the first, that 1, you add 1 and you get 2. So now that you have all those exponents plus 1, you have you multiply them together like 4 times 2 times 2. So back to the next slide again. So when you are given this question, you would want to get the prime factorization and add 1 to each of the exponents and calculate the product. Cool. Let's move on to the next question. So now here's a hard question. So the question is, yep, you can go on to the next slide. What is the sum of the factors of 680? You can think about this. I'll give you maybe a minute to think about this, and we'll probably go into this because the brute force way, which is adding all the factors, takes a really long time. But there is a somewhat more clever way of doing this. And you can see, yeah, thanks for going to this slide. You can see I kind of wrote all the factors here on the right side. And there might be an interesting way to add them, an interesting way to calculate this right side. So let's, does anyone have any suggestions of what you might do to simplify this right side? Yep, Isabel?
Like combine all of the similar terms, like combine all the 2 to the power of 1 or like the 2 to the power of 3 or 7 to the power 17 to the power of 0, but it just goes 1.
Yep, that's actually perfect. So you can see that there's a lot of like terms, and the way that I went is I combined the 17s first, but you can, like Isabel did, combine 2s first. But let's say you combine the 17s first, you would get this. So you can use the distributive property, right, to do that. And then you can see that the two sums are the same when you factor by 17 to the 0 and 17 to the 1. So then you can combine that together again. That's like, I guess, reverse distributive property. And you'll get this. So, so from here, anyone have a suggestion of where to go? So we've simplified it a bit. Is there any other way to simplify? Someone have a suggestion? Maybe not Isabel. Maybe Jaden, any ideas? Maybe, no. Audrey, any ideas? Yep, so Audrey told me do the same thing for the 17s, but for the 5. So you can also use distributive property, or basically take out the like term, which is 5 in this case, and group it like this. And you'll see that that's the same sum again. So you can also just combine it like this, and this whole thing is really just this. So yeah, so this is one cool way of figuring out how to get the sum of all the factors. Please send me in chat what the result of this is. So from here, you still have to do the math, I guess, and figure out what the number is here. So let me know what you guys got.
Someone's raising their hand. Okay.
Yes, Kaden.
I have a comment. So I think I actually know the formula for it, but it's a little bit complicated.
All right, what's your formula?
So it's like once you find the prime factorization of the number,
Mhm.
You take like the number and then you raise it to the power of like, so like for 2 cubed, you would do like 2 and then you raise it to the power of like the exponent plus 1.
Mhm.
So it would be like 3 plus 1.
Mhm.
And so that would be 2 to the 4th. And then you subtract 1.
Mhm.
And then you divide all of that by the number -1, so that would be 2 minus 1. And then you do this for each of the prime factors, and then you multiply all of them together, and then that should give you the sum.
Okay. That is interesting. I don't know if it completely works. So you do 2 to the 4th, then you say divide by 1, -1 also divide by 1.
Yeah, so it'll be 2 to the 4th over 1, and then you multiply that by 5 squared over 4, and then 17 squared over 16.
I think it works. Why does it work? Can you explain it?
I think I forgot the proof.
That could be a cool exercise. Yeah, I think that's a really good way to do it too.
All right. Getting some answers. All right, so yeah, let's just keep going. So you should have gotten 15, 12. And so that's adding all this together. I think actually I did it wrong. So the answer is actually 1620. The leftmost number isn't 14, it's actually 15. So there's a typo here. 1620 is the correct answer. And yeah, so let's go to the next slide. Yeah, so in general, I think Caden has one interesting idea, but I'd like to at least explain the idea that the textbook explains, and also which I think for me makes more sense. So what you can do is you can have the sum of basically all of the prime factors, basically like you see here. So 2 to the 0 plus 2 to the first plus 2 squared plus 2 to the third. Add that all together, then multiply 5 0 plus 5 the first, right? You keep doing this. This will work for any prime factorization. So, and this should make sense because if you think about this, when you're doing this cross multiplication, you're getting every single combination of 2 to the whatever times 5 to the whatever, and it ends up being a factor. So this is very similar to when we were looking through all the different paths, right? And you can think of it like, oh, instead of just having these paths, they kind of really look like, you know, you're adding them together and you're cross multiplying. So going through a path here and adding it all together in the end is just like cross multiplying across all of these. So that's why this actually works. Does anyone have any questions or comments about this? Hopefully you can kind of visually see what's going on here. So yeah, the general rule is you take all of the exponents for the prime factors all the way up to the highest. So 2, 0, 2, 1, 2 squared, 2 third. Add that all together. Then you do this for each one, and then you multiply all this. So this is one way to do that. This is the general rule. And yeah, so let's continue. Let's go to the review round. I'll just make sure that, you know, everyone's paying attention. So first, let's find the prime factorization for 13. Please send me your answers.
He is 14. You really? Hey, it's 14. 8, 8.
Cool. All right. So the answer was it's basically 13 to the first, or just 13. And just be careful of sometimes, I know some people might put 1 and 13, but 1 isn't a prime, so just be careful of that. Next question, find the prime factorization for 36.
I can't really put exponents in the chat, so can I just like write it out? Like
Yeah, whatever. So some people, what they might do is you might use a caret to symbolize an exponent. Or you can just write it out, whatever works for you. All right. I think most of you got this. So it's 2 squared times 3 squared. And yeah, the next question is finding the number of factors. So, and if you get this quickly, you can also start thinking about what is the sum of all the factors.
We're back in a bit.
Okay. All right. So, yep. So Coach Owen's not able to do this, but the number of factors should be 9. And that's because it's 2 squared times 3 squared. So you add 1 to the 2, you add 1 to the other 2, and you multiply that. So that's 9. Now, okay, he actually is here. Cool. So yeah, this is the reason why. And you can also now start thinking about the sum. Some of you have sent it to me, and good job. But yeah, for everyone else, please get the sum for the factors of 36. All right, let's move on. So, yep. So one way of doing it with the shortcut that we learned is you can do 2 to the 0 plus 2 to the 1 plus 2 squared times 3 to the 0 plus 3 to 1 plus 3 squared. And you'll get 7 times 13, which is 91. So, all right, let's do a bit of team round. What I want everyone to do this time is questions 10 through 20, but you probably won't have time for that. So just do as many as you can. And yeah, we'll get back in 3 or so minutes. Cool, you can create the breakout rooms. So yeah, start at 10. If you want to challenge yourself, you can start from the back and go. So start at 20 and then go towards 10.
Coach Owen, are you making them?
I'm trying to find who goes in which room.
Okay, you can just randomize it too. It's fine. I think the boys who are at school, they can just be their own group. There's already
Uh-huh.
4 of them. Yeah.
Makes sense.
You guys can start.
Yeah, you can start working on the problems also.
I can start
As
working.
we're assigning you.
Assigning people. Okay. Hey guys, Brian, Jason, Logan, Caden, are you guys there? Okay, sweet. I invited you guys to your own breakout room. So if you accept that, you'll pop into it.
Good job, Owen and James.
Thanks. Man, it took longer than I thought again.
Did you make those slides for the PATs?
The which one?
The PATs?
Yeah.
That was a good idea. I liked it. I think I would teach it that way too, because otherwise, I don't know. Sometimes I tell them just like options, like, oh, this is like a marble, a bag of marbles. This is another bag. This is another bag. But I like pass. That's a good way.
Thanks.
Caden's solution was a simplification. He algebraically rearranged the formula. I think he saw that before.
Okay.
But it was good to explain the paths because that's the reasoning behind why it works.
Right.
I wasn't sure about the division part.
It's
Is that
sum of
true?
geometric series. It's a minus 1
Oh,
a to the n plus a to the n minus 1 plus a to the n
that's
minus
the number of
always
terms. Right. Okay.
And then
Yeah,
you
no, that makes
to
sense.
find that sum, you just move this underneath.
Yeah, that's smart. Wow. Okay.
I don't remember this stuff. I checked it manually and I was
That's
like,
good.
oh,
That's
okay.
good. No, that's pretty cool.
Jasmine, do you think we can give them like a AMC 8 sometime to try?
Oh, I do give it to them. They're already doing
okay. Do they like it?
it. Maybe. I think they're a little discouraged that they can't do that many problems yet, but that's just how it is in the beginning. You do like 5 or 6 and then you get better. I think they're some of them have never done competitions before, so they're so used to getting 100%, on their math test. And like this is not like it, but it's good. I tell them, maybe I need to remind them, like, we are stretching our brain. I don't know, or like we are learning.
I could share we could share stories of how we did. I got 1 question on the Amy my sophomore year.
Oh yeah,
I got 1 out of 15. So
I know, it's just about, you're supposed to just enjoy the process of learning. Yeah.
yeah, it's also motivational for some of them. I think it was motivational for me to like try to get a high score and improve.
Yeah,
Um,
yeah.
But it is like a completely different score distribution.
Hmm.
Yeah.
Yeah, yeah, for sure. Yeah.
Um, the link was hard to see. I took some notes. The reason I didn't see it was because I have 3 windows open. I have one for participants, one for chat, and one for the screens, so I could see
Oh,
if you're raising hands. And it covered the Y.
Oh no.
So I didn't notice there was a difference between the 2 consecutive slides.
Mm.
So I think 2 solutions is we can either reserve like the rightmost 1/3 of our slide, because we don't need that much space per slide. We could reserve like the rightmost 1/3 of each slide to be blank. Or we can just paste things into slides, like screenshot and paste from the web resource.
Um,
So those are 2 things I thought about.
or maybe just try to have links on the left side.
Or that, if we reserve the rightmost 1/3 as blank, that allows the person who's helping to like keep track of stuff in such as chat and windows without covering up the content too.
But
That-
that's
so
a
that
good
was my-
point, but I think it might be a little weird, like showing the slides. So
Okay.
yeah, I think I'll just try to have the links in the left side. But usually I won't have a link. I feel like for the most part it'll probably be just all the slides. So I just thought that that was a pretty nice. I didn't want to copy paste all that to the slides, so I just had a link. Okay, I think actually it's about time. We can probably close
Yes,
the
I'm
rooms.
finishing
Well,
up.
last thing, or I was gonna ask Owen, you can close it still. Is the kids emailing you their solutions?
They didn't for this last week. I
Oh,
think
okay.
it was
Too tough.
more roundabout and more proof based.
I
But this
see.
week we'll have a cool challenge problem.
Okay, cool, cool, cool. Okay, I'm gonna leave a little early because I'm gonna help my brother with something.
Okay.
But
Right. Bye,
yes, you guys
Esteban.
did great today.
Thanks. Yeah, I'll try to leave I think in general we should try to leave more time for the team round, and I did not do that.
Hi, welcome back.
Welcome back, everyone. Um,
You can
sorry for the brief team round. So yeah, I think we'll be sending the solutions through email as well. But here's honestly, yeah, well, let's just skip through that. So here's the challenge problem for today, and also um, please send me something that you learned today, and then everyone is dismissed.
I'll read it aloud while we're here, but you guys can read ahead. So the challenge problem is 17s and 23s related to what we're learned today. So let's call a number flowing if every pair of consecutive digits in it forms a 2-digit number that's divisible by either 17 or 23. And the question for this week is how many 2021 digit numbers are there that satisfy this condition? So here are some examples of smaller numbers that are considered flowing, right? So you have 234. This is a flowing number because if you read the two pairs of digits consecutively, you get 23, which is divisible by 23, and 34, which is divisible by 17. So this checks out. 8,517 is also a flowing number. So you have 85, 51, and 17. And all of these numbers are divisible by 17. And lastly, we have 4,629. And this is not a flowing number because the first pair, 46, it is divisible by 23, but neither 62 nor 29 are divisible by either 23 or 17. So that number doesn't count. Is that clear? Does anybody is confused or questions?
Yep, feel free
Go ahead.
to. Arish, you have a question?
Yeah, what does it mean 2021 digit numbers? Does it mean that a number that has 2021 digits?
Yes, it's a number that has 2021 digits. Your answer, here's a hint, your answer will not be very big. It won't be like crazy big. So I'm not expecting you to spend all week on scratch paper doing this.
Your answer will probably not be 2021 digits long.
A thing to notice, so as you guys do the AMCs and math competitions, right? Oftentimes the authors will put in numbers such as like 2021, like a crazy big number, right? Relating to the year we're in or something. And that is a hint to you guys that that number does not matter. They picked it arbitrarily. They picked it randomly to scare you. So if I'm asking you for how many 2021 digit numbers there are that satisfy this, it's a good sign that solving this problem doesn't depend on the number of digits in that number. There is another way. Cool. And that's it from me.
Another minor thing is a lot of math competitions like to use the current year. So knowing some facts about the current, like that number is useful. So if you knew like next year, 2022, if you know the prime factorization of 2022, that sometimes comes up. So
And Coach Roma, you'll send out the answers to the review round, or sorry, not the team round
sure,
afterward.
yeah, I can do that.
Cool. That ends our session this week. Thank you guys all for coming. And remember to send Coach Roma something cool you learned today.
Yep, see you guys. Well done, everyone.
Bye.